The dynamic system for our quadcopter is an input-output model that seeks to maintain a self-leveling platform. Using an accelerometer to measure both static and dynamic acceleration forces, the quadcopter maintains the speeds of its four rotors to keep the aircraft stable with self-correctional flight. Upon startup, the accelerometer has been programmed to automatically calibrate itself by storing its current state as its initial body frame. Assuming that you place the quadcopter on a flat surface, the initial body frame is now parallel to the flat Earth frame. There is now a relationship between the two coordinate frames. The accelerometer measures both the static force of gravity to determine its orientation with respect to the horizon, and dynamic forces caused by each of the four contra-rotating rotors of the quadcopter. This is a continuous system that is constantly providing data, allowing our state variables to change continuously over time. It does this at the bandwidth of the accelerometer of around 300 Hz.
The forces that govern and influence the dynamics of a quadcopter during flight are pretty simple. They are the lift forces produced from its four propellers and the force of gravity due to its weight. The direction of the force of lift is perpendicular to that of the propellers. As lift is being generated, a moment about the quadcopter is also being generated from the lift. The moments experienced by the quadcopter are the results of the differences of forces between the opposite propellers multiplied by the distance that they are placed from the center of mass. For the angular motion experienced by the quadcopter, the equation of motion is given by torque equals to the moment of inertia about the center of mass multiplied by the angular velocity. In order for a quadcopter to be hovering in a state of stable flight, the lift forces produced by the propellers must equal the weight of the quadcopter. In addition, the moment produced by the lift forces of the propeller must have net moment that is equal to 0. Adjustments to the roll movement is acquired by a difference in moments due to the decreasing and increasing speed of opposite propellers. When the quadcopter is tilted, it can measure an angle between the body frame and the inertial frame. This is a Euler angle which can be further analyzed by turning into a quaternion and eventually into a state space form.
The rotational acceleration of the rotors is controlled by manipulating the current supplied. The inputs of this system are the dynamic and static acceleration forces that are measured from the accelerometer, though the dynamic forces are manipulated via directional and throttle inputs from the transmitter. This outputs pitch, roll, and yaw angles and compares these to the initial body frame. The current acceleration forces are continuously measured and calculated into state vectors. The feedback that is being used for the control loop is an error calculation of the desired orientation of the initial body frame and the current orientation. This controller error becomes an input for a PID controller. For this quadcopter, a P-only control law is used. It is the simplest algorithm in the PID family that repeats a measurement computation action loop. Only the proportional control is utilized, hence P-only. The motor current is set in proportion to the existing error. The integral and derivative components are not utilized, and so to correct for error accumulation and prediction, manual input is required. This is accomplished with the trim function on the transmitter. The trimming function allows the user to calibrate the quadcopter if it starts to drift due to overshoot from error accumulation. The derivative component of PID aims to flatten the error trajectory and improve settling time, but in this example it is not utilized.